Thank you for having me. This is joint work with Josh Blumenstock at the Information School at UC Berkeley. And I should also point out Samson Knight is a graduate student working on this project. He's been doing an amazing job, and he's here at the conference. So machines are being used to make lots of decisions that used to be made by humans, ranging from credit decisions to decisions in the judicial system, who receives a loan. Let's see, nope. What information is important, for example, Google search engine results or Facebook rankings as well. And let's see. It is a beautiful slide. Great, so across many different domains, machines are being used to make important decisions, who's hired as well as who receives humanitarian aid. In all of these cases, some aspect of an individual's behavior, some X, is fed into a decision rule to make some decision Y. And so we're going to think later on in this talk about the decision to provide digital credit in developing markets where we don't have traditional credit scores, and we'll have as a running example the decision to receive a loan as a function of some other information, for example, the number of Facebook friends you have. In these types of decisions, there are two big problems. And the first is that once you start making consequential decisions based on this information, people have incentives to game that information and game that algorithm. So their behavior now is also a function of this algorithm. The X's are now a function of the Y's. And in our examples, obviously, you could, if the scoring rule is based on the number of Facebook friends you have, you might be able to game the system into giving you a loan by adding more friends. Firms spend billions of dollars trying to optimize their position in Google search results. And there's this back and forth war in spam filtering. And the second issue is that once we're making consequential decisions based on this type of information, people often want to know, why was I denied a loan? Why was I not released from the system, et cetera? And there's been a big push towards a right to explanation. But the more information you give about the inner workings of these algorithms, the more problematic this first problem becomes. And it could potentially undermine the application of machine learning in many of these applications at all. This is a project that asks the question, can we build decision rules that function even when the algorithm is fully transparent? And to do that, we're going to develop a new theory, a method, which is going to solve for equilibrium decision rules, anticipating manipulation, given the costs of manipulation. We'll then have an experiment to actually estimate this model, where we estimate the cost of manipulation and test the performance of our more robust algorithm. And this is a field experiment in Kenya designed to mimic digital credit. And we're going to spend about half of the time of the talk on each of these components. And I should flag that this is early stage. The experiment is still running. We'll have some pilot results for you. So feedback is very welcome. So this problem of manipulation is problematic across many applications of machine learning already. And firms have figured out some way to deal with it so far. And we're going to call that the Silicon Valley approach, which is quite common. And this is to keep your algorithms hidden and secret so that people can't inspect them, and then periodically retrain them, because you realize that some information about their workings may eventually leak out. And so I might see some initial data, x0, train my model against that, and then every month or every quarter retrain that model as people game against this. This, of course, exposes you to substantial risk over this learning process, and it might not reach an equilibrium. Our central insight here is that this looks like a process of equilibration. Economists know a little bit about equilibration. Can we instead just solve for the Y star that works best, anticipating that people will best respond against it? We're going to focus on linear decision rules for clarity. And the estimator we come up with is a new class of linear estimator. And if we think of OLS as maximizing in-sample fit, we have other estimators where we've sacrificed in-sample fit in search of another objective. Instrumental variable sacrifices in-sample fit to obtain a causal estimate of betas. Penalized regression says, if we just maximize in-sample fit, that might not do well out of sample. So we want to maximize out of sample fit when we draw a sample from the same population or environment. Our notion of fit here, we're going to call strategy robust. And we want to maximize out of sample fit not from the same environment, but in a counterfactual world where this decision rule is implemented, used to make decisions, and manipulated against. Now, this connects to a lot of theory. Obviously, the Lucas critique is what we're dealing with here. We're trying to model it and come up with a solution in a particular application. There's a lot of work in computer science, in adversarial machine learning, and strategic classification, which outlines kind of contours of some of the theory of this problem. There's also some theory in mechanism design about the muddling of information, which outlines some of the theory as well, and some other papers that are related as well. We're creating an empirical model here and estimating it for the first time. So in our model, a policymaker wants to give a set of individuals different rewards. So each individual I will be given, or ideally would be given, a reward yi based on their underlying type, theta I. And so this would be what ideally the policymaker would do. They would see an individual's theta I, and they would assign them a reward based on that. But our policymaker doesn't see an individual's theta I. They see some behavior, xi, which is related to that. And so the policymaker has to give out rewards based on this behavior that they observe. And here you could think where yi could be creditworthiness, and x might be Facebook friends. Now, an individual here receives some utility from this decision. And so they have an incentive to receive a higher reward. And they can also manipulate their behavior at some cost. Individuals like having their behavior at the bliss level. They like to set their x's at their thetas. But if there are incentives to, they can manipulate that behavior that is exposed to the algorithm. They face quadratic costs, and those costs can differ in two ways. First, some people may find it easy to manipulate everything, and others may find it hard. So there's difference between people. And there's also differences between features. So some features may be easy to manipulate, like it's easy to make a lot of different outgoing calls. It's harder to make a lot of incoming calls, or to receive a lot of incoming calls. So then, given this model, the behavior that we observe individuals make is actually a function of this beta. So if our betas are 0, if we haven't implemented a decision rule, then our x's are going to equal our types, our thetas. But as soon as we implement a decision rule, they're going to deviate in a predictable way. And so what this means is that when we want to come up with a decision rule, if we just take a loss function that looks very familiar, which is a quadratic loss, this looks very similar to OLS. Instead of assuming that our x's are going to be fixed, we now assume that our x's are a function of our betas. And the model tells us exactly how they relate to beta. And so we can account for this shift. And we can embed this fixed point problem within our estimator. And this is when the policymaker knows the costs. And so a key part of this estimator is that we'll need to be able to estimate these costs. And we'll show you how we do that. So let's give you an example of how this can work. Now imagine a setting where we have two different features. And in the baseline types, this first feature is much more predictive than the another feature, but it's easier to manipulate. And if you did OLS, it would pick out, well, this initial feature, this x1, seems to be more predictive in the sample that I observe. And that works fine when it's costly to manipulate. But as you reduce the cost of manipulation, this performs extremely poorly. And you might think, well, we should just penalize this. You could use lasso. Lasso is going to do exactly the wrong thing. So Lasso is going to look at this baseline sample that you observe, and it's going to say, well, we should penalize these both, but x1 is more predictive, so let's kick x2 out of the regression first. Our method is going to weigh these things against each other. And if manipulation is very costly, it's going to approach OLS and put weight on x1. If manipulation becomes very cheap, it's going to shift weight to x2, even though in the baseline environment, that was not the most predictive feature. If we instead make x2 more cheaper to manipulate, you can see that our method is going to reduce the weight on it and also increase some of the weight on x1, compensating for that. And it'll also account for any cross-diagonals or off-diagonals. So it's going to use the information about the substitutability or complementarity of these features. So let's give you another example with some numbers. So this is another setting where we have one indicator that's quite predictive in baseline, but is very cheap to manipulate. And if you run OLS, you're going to estimate something very similar to the DGP without manipulation. And that performs well if there's no manipulation. Here it performs terribly if people can manipulate this rule. You could also think, well, we could just repeatedly apply OLS. So let's apply OLS and then retrain it on the new data and go back and forth. In this case, that doesn't work well at all. You just end up bouncing between two different extremes, neither of which does very well. And this is even in the case where there are no frictions on learning. In contrast, our approach is going to place lower weight on x1, and that's going to give up some performance in this sample that we observe. So in sample, we're sacrificing performance, but we're going to do a lot better in the case where there actually is manipulation in this counterfactual world where this decision rule is implemented. So we developed this with one particular application in mind. There's about 2 billion people around the world who lack bank accounts. But in the past few years, two innovations have come along. One is mobile money, which makes it very cheap to give or send money. And the second is an observation I made 9 years ago, which was to suggest that even though most of these 2 billion people lack credit scores or any formal financial history, behavior in just how they use their mobile phone can be predictive of whether they repay a loan. And so mobile money coupled with this alternative credit scoring has sparked a new industry of digital credit, which has taken off to phenomenal scale. In Kenya, over $2 billion has been dispersed through digital loans, and 27% of Kenyan adults have taken out one of these loans. Kenya has been at the forefront of this, but you see this spread happening across the developing world. There are over 68 products worldwide as of the last count, which was 2 years ago, and I'm sure that number is far higher today. So one problem that's come up in these implementations is, of course, manipulation. And people are reverse engineering these systems. So here's an anecdote from one of the firms we're working with. A male user was told he was denied credit because he didn't have enough Facebook friends. And so you see him adding Facebook friends each week, and he kept getting denied. And then they see that his friend count jumps, and he's approved for a loan. And the reason was that he'd changed his photo to be that of an attractive woman and managed to befriend a lot of people. And so this is one of many cases of fraud. This is a kind of cute-sounding one. There are others that are far more problematic for these firms' businesses. This firm no longer tells people why they are denied credit or reveals the algorithm. And so regulators are now concerned that a large part of the financial system is not providing any transparency about how these decisions are made. And so again, we see these two things in tension. So we designed an experiment to try to address this problem. We're working together with the Busara Center for Behavioral Economics in Nairobi, Kenya. And we designed an app which is designed to mimic this situation. It collects the same data as a digital credit app. So you install it on your phone. It will log anonymous call metadata, what apps you install, battery charging patterns, and location patterns. And I want to be clear that even though this is anonymous, this is data that could be sensitive. So we're very clear that about providing informed consent, and users have many opportunities to opt out of this. this is a setting where the Busara Center has worked with this population a lot, and they've built a lot of trust. And so a lot of people are very happy to be a part of this study. And you can see it's kind of a fun design. And the second thing that this app does is it makes consequential decisions based on your behavior. Our initial idea was to infer a person's creditworthiness and then make them a loan. So do exactly the same thing as a digital credit app, but it turned out to be hard to start a bank. So we're doing something else which is a little bit easier, which is to try to infer other characteristics about an individual from the same data and then provide a grant based on that. And so, for example, one of these challenges that people receive is you will receive 250 Kenyan shillings if this sensing app guesses that you are single from the way you use your mobile phone, or college educated, or unemployed, or female, or any other number of ground truthable indicators. The full study is in progress with about a bit over 1,000 people, but we'll give you a taste of what we're going to get from the pilot results. So this is what it looks like when you install the app. You agree to give it permission to read some of the data on your phone. And if you do, every week you'll get a challenge. And so here, this week's challenge is to use your phone like a single person. This is not going to tell you how the algorithm is making that determination. So this is an opaque challenge. Some other people will be randomized to be told exactly what this decision rule is and be given a tool to help them calculate their payout so they really understand. And so our study has a few parts. So we're going to survey people to get these baseline characteristics, these ground truths, these YIs, and then observe their behavior prior to implementing this decision rule. And so at this point, they don't have incentives to manipulate their behavior. We can estimate these thetas. Then in the second part, phase one, we're going to give people simple challenges. We'll pay people to manipulate one dimension of behavior, like outgoing calls or incoming calls. And that's going to allow us to estimate the cost matrix, which will allow us to estimate both a lasso model and our robust model. Then finally, in the last phase, we'll test these models against each other. We'll test them both under opaque treatments, where we don't tell individuals what the underlying decision rule is, and transparent rules where we do. This allows us to estimate the gain from the robust model in transparency. It also will allow us to estimate the equilibrium cost of transparency. If you thought that you could keep these rules secret and obtain higher performance, then we'll be able to tell you what the performance loss is. We can actually compute that object just from our model before revealing anything about before revealing the actual decision rule. I'd be happy to talk about that more. We have a bit over 100 indicators, and you can see there's some correlation between them. And these are correlated with some of these ground truths. So we can predict someone's age with some error, whether someone's gender, their employment status, et cetera. In phase one, we also try to incentivize people to manipulate these behaviors. So paying people for each different call, the person that they call each week. And you can see when we pay people for that, their calls out goes up. And you also see changes in related behavior, which is going to allow us to estimate these off-diagonal parts of the cost matrix. If we instead pay people based on incoming calls, you can see in the pilot we had a lower effect on that, but it looks like in the right direction. And so we do this for a series of different features. We can estimate the responsiveness of people to these different incentives. Then we'll come up with some decision rule. And so here to start, we found that college-educated people tend to use Twitter and tend to make a bit longer calls. And so we might have this as a decision rule that comes out of this. And if we incentivize people, use your phone like a college-educated person, and don't tell them what that means or how the algorithm is going to decide that, you actually see pretty noisy results, and people's Twitter use seems to go in the wrong direction. If we tell people exactly how they're scored, in the pilot we actually saw people go in the right direction. So people seem to use Twitter more, though that's very slight. So overall, again, the problem is that manipulation can undermine the use of machine learning in many settings, and it also provides justification for opacity, which might not be desirable in many settings. This project develops both a theory, a new method to solve for robust decision rules, and a way to estimate these models, and an experiment that actually demonstrates how that could be done. One key object that this estimation requires that's new is this cost matrix. And so the experiment is one way to do this, but we're also working on alternative ways to do this, whether eliciting estimates from experts or using the correlation structure in behavior in a more structural way. Thank you so much for having us, and we look forward to your thoughts.